time again. This is the second video of Chapter 2 of CNBT 1311, Spring 24, 8, Week 1. If y'all are still alive and with us, which I hope you are, let's start off with structural equilibrium. This will be page 12. This is still tracking. All right, we talked about these force vectors, okay? So let's get a definition. In both structural design and analysis, we're concerned first with the magnitude, direction, and point of application of forces. Again, this is statics, and their resolution to produce a state of equilibrium. Now, what does that mean, a state of equilibrium? Well, let's make sure this is actually working. Yes, it is working. State of equilibrium. Equilibrium is a state. Equilibrium is a state of balance or rest resulting from the equal action of opposing forces. Now, you've all probably heard of an equal and opposite reaction. So if we have a force vector going in that direction and we have one going in this direction, and both forces are equal, then nothing's moving, right? Doesn't move. And if one force gets greater than the other, then something's going to move. All right. All right. For a rigid body to be in equilibrium, two conditions are necessary. First, the vector sum of all forces acting on it must equal 0, ensuring translation equilibrium. Now that all sounds really geeky speak, doesn't it? In other words, the forces have to balance or it's going to move. Now we don't want our structures to move, do we? No, we don't want them to move. So we want them to be in equilibrium. And so second, the algebraic sum of all the moments of the forces about any point or line must equal 0, ensuring there is moment equilibrium. So we have static equilibrium and we have moment equilibrium. And that means it's not rotating. We don't want our buildings to rotate. So the rotation, this is moment, that's rotation, those have to be resistant. So if this is a cantilever, just like that cantilever retaining wall, it's just like the moment arm or the wrench, right? So let's presume this is an overhang on a building and it has weight. It has the dead load and maybe it's got a live load. Let's say this is a fancy balcony and here's the old gray-haired man standing out here smoking his cigar. Okay, here we are. I'm smoking my good Churchill Perdomo 12-year aged in bourbon barrels Maduro, and I'm smoking my cigar. Okay, and I've got my glass of bourbon over here, and I'm just enjoying myself. And of course, this is my house, and this is the balcony, and I'm overlooking my kingdom. Okay, I know I'm being silly. All right, so we have a force, right? Because it's cantilevered. This thing is stuck in a wall or it's built back a part of the floor. If you're a smart architect and you got a good structural engineer, this would all be a part of the flooring system. And we'll get into that in a little bit. I'm getting ahead of myself, okay? So this force is counteracted by what the flooring system can do. But now that I've confused you and I've added more stuff to this than I need to right now, let's get rid of that. Let's get rid of this. Okay, and I'll quit being a geek. Well, maybe not. Can't help myself. So, if we have a force going this way and it makes it want to rotate in that direction, we have to have a resultant force resisting that, right? So these two rotations have to balance, okay? Now, taking the bolt off with that wrench up here, we don't want it to balance. The torsional resistance of the bolt we want to overcome by the amount of force we put on the fulcrum. And that's all a cantilever is a fulcrum. All right? Okay, so that's all I'm talking about here. Okay? Now, again, this is not a structural engineering course, and I am not going to beat you up over this. I am not going to beat you up over this. Now, Sir Isaac Newton, in his Principia of Mathematica, which he did in the late 1600s and was finally adopted by the Academy of Science in Paris in the early 1700s, his third law of motion, the law of action and reaction, states that for every force acting on a body, the body exerts a force having equal magnitude and in the opposite direction along the same line of action as the original force. Now, that's statics. Okay? Newton's third law. Okay? A concentrated load acts on very small areas, or a particular area. Like this would be a concentrated load on the end of that beam. Okay? The floor loading is a uniform load. Okay? Uniformly distributed load would be like floor loading up here. This is a uniform load here. Okay, it's uniform. It's acting all the way across that beam in a uniform manner. Now, one of you smart guys and gals are going to go, well, wait a minute. There's less load here than there would be if it's out here. And that's right. You make an assumption it's a uniform load. But if it was a concentrated load right here, then you wouldn't have uniform loading. Okay? I have probably confused you, and I apologize. Where's the eraser? Make it work. Make the eraser work. There we go. Okay. All right, let's get all this out of the way. Okay, so let's go back. Get back into the script. So a concentrated load would be represented here. The end of the beam that's carrying this uniform load. Okay. And we have this 4 panels that are going uniformly loading this beam. We have this loading that beam. Okay. So how would you do this? Well, you got half of these, half of that uniform load going to this uniform load. You got half of this uniform load going to there, and you got half of this uniform load going to here. So that center beam, this one's got to carry twice the uniform load that carries, right? Okay. So uniformly distributed loads, concentrated load, these are terms that you need to understand. And then you have what's called a free body diagram. And I don't know why they get so deep into the weeds on this, unless they're preparing you for statics, which is really a separate course. All right, so free body diagram is a graphic representation of the complete system of applied and reactive forces. Okay, so an argument could be made this whole thing's a free body diagram. Okay, and structural engineers, they go through this. We sit down and look at the building and go, okay, we start breaking it apart. We've got loads for the foundation that has to resist because both of them are going down like that and up. And then we've got balance forces here. We got to balance the forces here. And this is all static. We're not talking about the bending load on that column, or whether that column might bend out like that, okay? Or that column might bend in like this, okay? So, or what's this beam going to do? Well, this beam is going to want to bend down like this, sort of like that. And this beam will want to bend in a manner like that. Okay, and then it has to resist that bending. So this whole thing is a free body diagram, and it's just simply a graphic representation of how the complete system is going to work. Okay? All right, enough of that. So here are definitions. Concentrated load, uniform load, free body diagram. We can get deep in the weeds on here. Columns have to do what? Well, columns are rigid and relatively slender structural members. All right. They've got to take care of axial stresses. That's a fancy word for the stress down the longitudinal axis of the column. They have to take care of bending. And here's a term: kern area is the central area of the horizontal section of a column or wall. And it's really the center of the stresses. So sometimes if you overload a concrete column, they'll start falling out because they're compressing. The reinforcing rods in here are bending and concrete's popping out, and really bad things happen. Long, slender columns are subject to failure by buckling rather than crushing, which makes sense. The longer the column for a given area, given size, okay, makes it want to bend as opposed to crush down, bend and break out. That's called the slenderness ratio, or the K value. And there are all kinds of engineering things we have to worry about. The length and the radius of gyration, and these all sound really scary, but don't get all scary. Radius of gyration, or R, is the distance from an axis at which the mass of a body may be assumed to be concentrated for a column section. The radius of gyration is equal to the square root of the quotient of the moment of inertia. Now, oh my God, I know y'all are running for the door. Don't worry about this, okay? Don't worry about this. Engineers worry about this. Structural engineers worry about this, okay? When we go to look for a column or a beam, we start looking at radius of gyrations. They're in a manual. They're in a book for a given type of a structure, whether it's a concrete column or it's a steel column or beam. It's in the steel manual, or it's in our concrete manuals, and we calculate that, and it goes into the slenderness ratio and the KL over R. KL over R is, we look at, and you're not going to be tested on this. You're not going to be tested on this. Don't freak out. Okay, all that goes in to how skinny is the beam or column, how resistant is it to bending. Okay, the effective length is the distance between inflection points in a column. The effective length factor, or K, see here's your KL over R up here, and your K factor. If both ends are fixed, they won't rotate, then your K value is roughly 0.5. If one end is fixed, it doesn't rotate, but the other end can rotate, then the K value is 0.7. If both ends are pinned, they both can rotate about their endpoints, and it's 1. And, what if it's like a flagpole? What if it's like a flagpole? Flagpole. Or a light pole. Okay, or a light pole. Or traffic light. Then the K is 2. All right. That's why you see these big light poles or traffic light poles that have the cantilever arms out. You know, the cantilever, those big arms out, and they got all those traffic lights hanging on them. Next time you're at an intersection, look at the base and see how they do the base for these things. Look at the base, see how they handle the base. Okay, because what this is going to want to do, right? That's pushing down, and so that's when I want to bend it over in this direction. And see, y'all are already structural engineers and you just don't know it. Okay, don't worry about this. I seriously doubt I am asking you a question about this geekoid structural engineering stuff. These definitions, they're fair game, okay, but they're in the book. They're in your beams. Okay, this is a uniformly an example of how we would describe a uniformly loaded beam. It's going to want to bend in the middle. It'll have a deflection point. This is your delta, your deflection, based on the stiffness of the beam. Bending moments inside the beam, and you got to worry about that. You'll get more into this in statics. I'm not going to be up on this course over this. All right. And of course, the longer the span for a given beam section, the less it can carry, right? The efficiency of a beam is increased by configuring the cross section. If you got a bigger, deeper cross section, then the beam can carry more. That's why if you just take, let's just say a 2x6, you're going to use it as a beam, a 2x6. Then the longer the span, the less it can carry. And the longer the span, the more it wants to roll over, it wants to rotate, lay down. So, what do you do in wood construction? Maybe you take a couple of 2x4s and you laminate them between a giant sheet of plywood. And you got 2x4s on the bottom that are glued, nailed and screwed to the plywood. Look at that. Alright. And we nail them, we screw them, we glue them. Okay. And now what have you done? You've taken multiple composites that can carry less load by themselves, but when you put them together and you make this super deep, then you've increased the load carrying capacity of what would have been just a single unit. They work together in consort. You've increased the distance between the top section and the bottom section, and it'll carry more load. And you see wood beams like this that are manufactured and used in construction. Apartment complexes, small commercial structures. There are companies that spend their entire business model making trusses and composite beams or carrying long span, and they're not as heavy as if this was one big giant piece of wood, as if you could find a tree that you could cut that piece out of. All right, beam spans. This is a simple beam, simple span. Okay. Here's your cantilever. We talked about that before. Here's all your definitions. If you overhang, you put a cantilevered overhang on a beam, then the beam can carry, it'll carry less moment in here. The moment diagram is smaller. If it's a simple span like that, or if it's a cantilever, so you've reduced the moment by sticking this cantilevered section out. And here's a double cantilevered section on a, or double overhanging is what he calls it. I call it a double cantilever. It's double overhanging, single overhanging, and a cantilever. Okay. Look, the moment in the middle gets smaller. Compared to this and compared to that. And so what would an architect use this for? Well, how about an overhang on a building? So if this was the roof structure, and it was a single-story building, and this was your wall going down the foundation, then what all have you done? You've got shading for the sun. Remember that part of the chapter before this? You've got protection, and you could maybe use this as a sidewalk or an entrance around. Okay? What if it's a multi-story structure? You've also got an overhang here, overhang there, and you have a balcony out here where people can go stand and smoke their cigar. Okay. All right. Now, so there are many ways you can reduce this. And just like I was talking about with the architect, this is how I solved this problem. He loved it. He got, so yeah. I mean, you can only span so far, and then, but if you make this all one monolithic, one piece of the structure, then you can play games with the moments and the shears. All right. Fixed beam ends. In other words, fixed beam means that this will resist rotation. That's all that means. It's a moment connection. It's fixed. It'll resist rotation. And so this beam that was pinned on the end that had a super high moment up here, super high moment, same span, but if you fix the ends, then the moment gets smaller, the bending gets smaller, and it theoretically can carry more load. All right. Multiple spans work the same way. Multiple fixed point spans. Okay. So we have fixed beams, suspended beam, and continuous beams over more than two supports. Now this is all one long beam. This is not like a bridge where at each one of these columns is an expansion joint. Those are all simple spans. But this would be like one long fixed beam, okay? All right. Now he is making a distinction here. A suspended span is a simple beam supported by overhangs of two adjacent spans. You see this right here, this joint? That would be like a precast concrete panel that was set in there. So this panel here is being supported by this overhang here and this overhang here, okay? All right, but if you made that one long concrete beam, then you can see how the moments are smaller, okay, than if it was fixed. And obviously right there in the center, it's really small, right? Because this is wanting to bend down and it's pulling this up. And this is bending down this way and it's kind of pulling that up. And that's a simple glide example. Trusses. I kind of drew you a truss with the force vectors. Remember the force vector formula? And there are all kinds of trusses, okay? And all these trusses have different names. The trusses are assumed to be pinned connections. It's a structural frame based on the geometric rigidity of the triangle, just like the geodesic dome. You have triangles, okay? And these forces travel down these triangles, okay? And they might come up depending on how you're loading this. Some will be in compression, some will be in tension, it makes for a lighter structural member that can carry a larger span. They use the term heel here for the lower end of the truss. The panel refers to any of the spaces within the web of a truss, okay? This is the web, and this is the top chord of the truss, and this is the bottom chord, okay? So the outer lines of the truss, be it on the top or the bottom, are called chords. All right. This is an open box truss. Now, this says zero force members theoretically carry no direct load, and their omission would not alter the stability of the truss configuration. This is wrong. Okay. Theoretically, it's correct. But what happens if you have a force reversal? Okay. Then you may need, then these might carry a load. But giving Ching the credit here, what he's saying is theoretically correct, that the way this truss is loaded, here, 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 and here, yes, this triangle carries no load. However, What happens if this is a railroad truss? Then we are going to have a load here. It's not a roof truss. Let's say it's a railroad truss or a road truss. Or there, right? Because we got the railroad tracks coming across here, and it's got to support it evenly across there. All right. So now in 609, in chapter 609, types of trusses and truss configurations. That's where all that you'll find your names of your trusses. Warren, Pratt, whatever. Now, just like that thing that I drew with the up here with the plywood, and where did you go? Oh, this there it is. Now, since I didn't save it yet, I'm not going to save these sketches to this. All right, there it is. Just like with this, what did I do? I made a truss. I designed a truss. That's a section of a truss. Back down to this open Bernadette truss. So let's cut a section. Pretend this is that two pieces of plywood. I mean that piece of plywood. All right. The 2x4s nailed on that. Okay. This is a solid diaphragm in here. But in this, to lighten it up, they cut holes out. Square holes, oblong holes, and round holes. These are called Vernondill trusses. They're frame beam structures having vertical web members rigidly connected to the parallel and top chords. So, what would these two 2x4s up here be called? That would be the chord. And that's the bottom chord, right? Okay. And this is the web, all right? Now, before you go drilling and poking holes in here, you got to be careful about stress concentrations. Safest thing is to have round holes to lighten them up, because depending on how you load this box, depending on how you load it, these corners here are going to have a high stress concentration. High stress concentration. That's why ship hatches are not square. Because in the corners you have a high stress concentration, and you have a tendency for stress loads to go this way and crack or have bad loading. So you want to make your hatches have round corner. All right. So if it's round, the stresses in the corners are distributed out. They're not concentrated on the line of just the corner. There's no extra charge for that. They found that out with Liberty ships during World War II. They were making them super cheap and quickly. So they would just have these square hatches in the hull. And when we got out in the rough seas, they found that the surface decking cracked along these lines. And the same way with concrete. You have square openings in concrete, you got to watch for cracking. And so the easiest thing to do is to put radius in your concrete formwork or an open hole. Okay? That way these stress concentrations in the corner are evenly distributed and not concentrated just on a point. Does that make sense? Okay. Worry about these definitions that are printed in here. Don't worry about the statics and the structural engineering. I'm not going to expect you to understand all that. Frames and walls. Frames can be pinned or they can be rigid. Metal buildings are rigid. That's why they call them rigid metal buildings as opposed to pinned. Frames and walls, a beam simply supported by two columns is not capable of resisting lateral forces. What are we talking about lateral forces? We're talking about wind and earthquake forces, right? Okay. If it's just pinned up here, it'll collapse like a cardboard box. You push on it and it'll switch over. But if you gusset these, you make these rigid connections, then they'll carry more load. And here's an example of a fixed frame and how it's supported as opposed to this one, which would just want to fall over. Here's the shear and moment diagrams of how that works. And right now that means nothing to you, and that's fine. Hinge frame is a rigid frame. In other words, it's rigid up here. It's fixed, but it's pinned down here. And if you just have a base plate, single base plate with bolts going into concrete, then we assume that that is a pinned connection. It would be something like this. Here we have a 3-hinge frame. It's 2 rigid sections connected to each other with a pin joint. It's more sensitive to deflection than either the fixed or hinge frame. The 3-hinge frame is least affected by support, settlements, and thermal stresses. Also, it as a structurally determinate structure, as opposed to this, and this means nothing to you. Structural determinant, don't get all freaked out over that. It just means it's statically determinate. You don't have to go into differential equations and use indeterminate structural methods to design this as you would that. Okay, and this is way beyond the scope of this course. Way beyond. You see this in super large commercial buildings where they might have a pin in the middle for expansion, thermal. A lot of your smaller structural buildings, rigid frame buildings, are like this. Okay. Takes an extensive computer model. You just can't easily sit down with mathematically determinate methods. You have to go through mathematical indeterminate structures to structurally design something like that. The computer programming now for these things is so prevalent. They kick them out. And you can see how this is rigid. See, so it's going to bend up here, but the bending is different because it gets to rotate around that point, and these beams can be a little smaller than if it was a total rigid structure. And if you'll notice, if you go look at a rigid structure building, you'll see that the gusset plates at these connections, they might be small down here, but the columns get bigger, and they have these bigger plates up here to connect to the upper structure, because all they're doing is just following these stress graphics. Okay? All right. Okay, so a load-bearing wall that acts as a long, thin column is nothing more than these frames up here with a solid membrane in there, solid diaphragm. So basically what you've done is you built your structural integrity in here, in between the two columns. So this whole wall acts as a frame. And you see that as a shear wall in tall buildings and in apartment complexes where you may have wood framing, but you'll have a center concrete column where the stairs are that go up through it, and they'd use that as the shear wall for the whole structure, much the way the pagoda center pole works. Very rigid wall, but it's not meant to snake dance like the pagoda. Any opening in a load-bearing wall weakens its structural integrity. So if this is made out of masonry, then you'd have a lintel up here. If it's reinforced concrete, then you would just put extra reinforcing steel up here. And you might put a radius. If this was poured in place concrete, this might actually have a radius on the opening as opposed to a square thing. But you can get by with a square thing as long as you engineer and design it and put extra reinforcing steel in there. It'll reduce that longitude and that diagonal cracking that it wants to do at a sharp corner. Plate structures. See how we doing on time. Plate structures. All right, plate structures are a two-way slab. Now, plates can be out of steel, they can be out of corrugated metal that are all welded to the substructure, or they can be in reinforced concrete. If this was reinforced concrete, then this would be a two-way slab. You have force resistance that way, and you got a force resistance this way. But you've got to account for being able to support it on all the sides, all four sides. Right? You got to transmit those forces to something. All right. So, plate structures. Rigid planar, usually monolithic structures. Monolithic means it's all one piece, like a cast-in-place concrete slab. And it could be a precast slab that's set, but as long as you're supporting it on the edges. You could pretend there are additional beams, vertical shear transmission in the plate. In between these imaginary beams, but the whole slab is, you just don't have these beams here. This is the main stress ribbon. The whole slab is reinforced, so it acts as a whole bunch of these stacked together that way, and a whole bunch of them stacked together that way. Okay. Talks about vertical shear. A plate should be square. A plate should be square. Across there. A plate should be square. Or rectangular even, but the more rectangular it is, down the long side, the narrower it gets on this side. It's a two-way slab if it's square, but if it's rectangular, it becomes a one-way slab, and then that takes care of, that's other structural issues. Again, this is basically just for you to come up with a set of vocabulary words. Folded plate structures. Folded plate structures are composed of thin, deep elements joined rigidly along their boundaries and forming sharp angles to brace each other. Each plane behaves as a beam. So each one of these behaves as a beam. Okay? Each one of these acts as a beam that's just at an angle. Now you've seen these before. And corrugated iron, corrugated metal that goes on a barn, folded plate structure. You take a piece of paper. Copy paper, and it bends like this, right? It doesn't support much. But if you fold that piece of paper evenly, right, then that limp piece of sheet, that limp piece of paper can support more load than it could if it was just a flat sheet. That's the way corrugated metal works. Okay, let's go back to the book. Space frame. The space frame is a three-dimensional truss, basically, okay? It's composed of sharp, rigid, linear elements, triangulated in three dimensions, and subject only to axial tension or compression. Axial tension or compression. Will a space frame take moment? Yes, it will take moment. Okay, but all of these elements in here are tension or compression, acting together in three dimensions. All right. The simplest spatial unit of a space frame is a tetrahedron having 4 joints and 6 structural members. Now that's beyond the elements of this course, but that is the structural mechanics of how it works. because the structure behavior of a space frame is analogous to that of a plate structure. Its supporting bay should be square or nearly square to ensure that it acts as a two-way structure. Okay, two-way structure. We want these things to be as square as possible so we have equal stresses going all the way through. Basically, space frame is a dimensional truss. Okay, going in all directions. Going in all directions. All right. You can Google space frames. Geodesic domes are a bent space frame, for a lack of a better definition, but we'll get to those later. In section 610, there's more information on space frames, and I designed several space frames. City of Houston used to have one over a city park over off of I-10. It was a basketball park, open, and what covered it was a space frame with metal roof on top of it. All right, where are we at on time? We're at 41. We're fine. Structural units, more definitions. You always start with the top and work your way down. What's it going to look like? Planks or decking. This could be a flat roof, or it could be a second story. Then you have your floor joist or your roof joist. A joist. What does a joist do? The joist goes between two supporting load-bearing walls or beams, and the joists are on beams or girders or on the top of a load-bearing wall. Slabs or plate structures on top of a bearing wall or on top of columns and beams. This is kind of a smorgasbord of building elements. Okay, vertical support, it talks up here for you. Your horizontal spans may be transverse. So I think that's pretty self-evident there. One-way system of joist. This is a one-way system. Okay. Joists are mostly one-way systems. If you try to make a two-way system using joist, you better be using a space frame or a concrete slab. So, and you would get your joist spans to be the narrowest span between your load bearing for your joist, be it a load bearing wall or a beam and column system like this. Here's an example of how you support a two-way slab. Two-way slab supported by columns. The problem with this is you've got to watch your shear loads on that two-way slab at the top. Just having a column coming up in a circular manner like that is you're probably not actually ever going to see that in reality. That slab would either have a shear pad like that at the column, and then the column would then rest into the shear pad, and this would be the foundation, and this would be the top part of the slab up here. So you got to watch the thickness around the column, because this is a stress concentration, and you don't want to punch through your slab. That would be bad. People would be very upset with you. So in the same way with the footing, that's one of those footings. We have footings go down here at the footing. If that was resting on just a thin slab on grade, that would be bad. In actuality, that column would probably go through the slab on grade and have either a bell or it would have a square footing. Okay, enough of that. Parallel nature of load-bearing walls leads naturally to the use of one-way spanning systems, of course. So you either use joist or you'd use like precast decking, precast concrete panels. And this could be a precast wall, be it a tilt wall or any kind of load-bearing structural wall. but in tilt wall construction, which we get to later. All right, a linear framework of columns and beams defines a three-dimensional module of space. Well, no kidding. You got columns and beams and walls and such. Two load-bearing walls naturally define an axial bidirection space, so which would make sense if this was like a industrial building and you had an overhead door. This was going to be an open bay with an overhead door, and this was going to be an open bay with an overhead door back here. Then your main load-bearing walls would be axial down the long length of the building. The benefit of this is it allows these two walls to be load-bearing, and it allows a shorter span for your roof structure and your joist. And of course, if this was an industrial building, you might have an overhead crane in here, and the crane would travel and be supported along the load-bearing wall. And this would be your crane coming across here with a little hooky deal on the trolley up on top. So if you just got two load-bearing walls, then we have an axial arrangement. If it's uniformly around all the sides, then it's two-way. All right. Look, 46. Structural spans. What happens after this? Lateral stability. All right, we'll go through structural spans, and then we'll make the next video on lateral stability. This is a rule of thumb. You go by what your structural engineer says and what the loading for your building is. But this kind of gives you an idea of what timber can do. All right, the spanning capability of horizontal elements, that would be this, okay, determines the spacing of their vertical supports. This would be your span. All right, the spacing and the scale of spacing is defined by the structural system of a building. All right, now, so let's look at this. Planks, that's just floor planking. I wouldn't scale this, but let's say 15 feet, depending on how thick it is. Most people are going to tell you don't go beyond 10 feet. But we all know that in floor decking for residential, you're looking at 24-inch centers. That's 2 feet, okay? Now, I don't know what kind of big planks these are, big timber planks maybe. All right, fine. But a joist, that would be the wood member on the strong axis, like this. All right. They say they can go up to 20 feet. Laminated beams are those wood trusses you make. Some of the commercial laminated beams theoretically can go up to 80 feet. But these things get super deep, right? Trusses can go up to 100 feet. Okay, this is timber trusses. All right, steel decking says it can go up to 10 feet. That's composite steel decking. That's not just metal sheets. Okay. Wide flange beams, they can go up to 60. Those are going to be deep beams. Open web joist can go up to 90 feet. I engineered some composite steel welded girders out of steel that are spanning over 100 feet for the Hardy Toll Road that you drive over every day over the Mopac yard. Because the railroad wouldn't give us a space to put columns in, so I had to get outside the engineering box and go into elastic design, which that was one of the first times that was ever done, and it worked just fine. I was a very nervous young engineer when we were loading the road up, but it all deflected just the way it was supposed to. It went really, really well. Concrete. Concrete's rigid. We know that it likes to want to break apart, but it has some flexibility. One-way slabs can go up to, what is this, 20 feet? We'll say 20 feet, 15, whatever. Again, this is a rule of thumb. Your structural engineer will guide you in your planning phase for your job. But this is a good place to start. Okay, it's a good place. It's a rule of thumb. Joist slabs, precast planks can go up, can have a longer span. Precast tees, those are your structural tees. Precast planks can be the pre-stressed planks that have the holes all the way down the longitudinal axis of the precast panels. These are precast panels of concrete. And they stack on top of one another, lock in like Legos. And this is a precast tee. And let's see, what is this? Flat plates. What is it? Two-way spanning systems. Okay, all right, two-way. This is a one-way spanning system. You know what a one-way spanning system is, right? Okay. And this is a one-way spanning system for concrete. All right, this would be two-way. Flat plates can go up to about 25 feet. I've designed some two-way concrete slabs that spanned about 25 to 30 feet. They get pretty thick, and you got to have double layer of reinforcing steel in them, but you can do that. Now, if two-way slabs and beams, if you've got beams in there, then they can go up to 40 feet. That just means this is all one concrete deal. This is the concrete slab, and a section would have a beam box that would look like this. Here's the upper part of this concrete slab. And then here would be your beam. There's your stirrups for your reinforcing steel. These are very expensive to form up. Your forming cost for concrete is your most expensive cost. And then here is your slab steel, longitudinal and cross longitudinal. And if it's a two-way slab, then you'll have an intersecting beam in this, at certain spaces going in this direction. Waffle slabs is just that. It's like a waffle that's flat on top, but underneath it's got little pockets cast in it. And what are you doing with those pockets? Look in here. This is your beam. Look, you got a two-way beam. It's just like a waffle. All right, so this is going to be video 3. We'll start with structural patterns. We'll start with structural patterns on the next video. Wow, this is 53 minutes. Okay, that ends